Okay, YouTube, in this video we're going to be exploring the multiplication rules for finding some probabilities here, or at least the rule that we use when we try to express the probability of a sequence of events occurring and how likely they are to occur. Okay, so before we go ahead and start in with our multiplication rule down here, we're going to go ahead and start by actually familiarizing ourselves with this phrase right here, and the phrase is independent events. Okay, and so we say that two events A and B, we're going to call them independent events if the fact that A occurs doesn't affect the probability of B occurring. And I give a couple of examples here, but we often look at situations where we have two things occurring in sequence. We want to find the likelihood that one thing happens and then the next thing happens, but these two events are independent of one another if the first one doesn't affect the second one. So for instance here, rolling a die and getting a 6 and then rolling a second die and getting a 3. The thing here is that this first die does not affect how that second die will actually roll. So the rolling of a 6 would not affect the rolling of a 3. So we would say that these two events here, rolling a 6 and rolling a 3, these are independent events. Just like if we were to draw a card from a deck of cards and get a queen and then put it back and maybe shuffle or something like that, but draw a second card in sequence and get a queen. The fact that you put that first card back means that the likelihood of grabbing a queen again the second time should be just the same as it was the first time. So the fact that the first thing occurred did not affect the probability of it occurring, say in this case, again. Okay. So when we use multiplication rules and probability, they kind of come out of the fact that things are happening in sequence. Okay, so when you hear these probabilities in this video, we're talking about things that happen one event and then another event occurs right afterwards and then another event occurs right after that. So we say the probability of two independent events, and this is pretty important here, two events where the first one doesn't affect the second one, but the probability of two independent events that occur in sequence, we say one must first find the probability of each simple event occurring, and then what we'll do is we'll just multiply our answers. So the example I give here is I say, well, what if we were to toss a coin twice? A coin is tossed twice. The probability of getting a head and then on the next one getting another heads, I'm telling you here is we just take the probabilities of each individual head there, so it's a 1 in 2 chance, and we'll multiply it by another 1 in 2 chance. And the reason why this occurs, and we can actually just list this out here, but when you consider the sample space for this experiment, remember the sample space is the set of all possible outcomes for this experiment. We have two coins here, and we say, well, how could these coins land? So it is very possible that they both land on heads, but it's also very possible that they could have both landed on tails. It's also possible, of course, that the first one landed on heads and the second one landed on tails, which is actually a little bit different than if the first one lands on tails and then the second flip lands on heads. So what we can see here is that the sample space, okay, remember we called the set of all possible outcomes the sample space. If I wanted to find the probability then that I get a heads and then a heads, and you'll notice I use the word and here, and this and would denote that these are happening in sequence from one another, not that they are both overlapping. And we say that heads and heads is this middle part. We do not mean that in this case. We mean that the first one happened and then in sequence the second one happened. But we say that the sample space for this is out of 4 possible outcomes. And we say, well, how many of these would give us just 2 heads? And we can say, well, easily, just one of these events out of 4 possible events would give us this. So there's a 25% chance. So what I want to do in this video is not so much make sense of this as much as I want to kind of indicate that when you look at this, I say the probability that you get a heads and heads, what we can do is we could re-express this, and instead of writing this word and here in the middle, this and that means things are happening in sequence, what we could do is we could just split this probability up into the probability of the first event, which is this probability heads here, change the word and to a multiplication sign, and then find the probability of the second event in this chain of events. And what that does is it kind of takes this having to think about what the sample space is here and reduces it to, well, we could just find the probability of heads as 1 out of 2 and the probability that it's heads here is 1 out of 2. And when multiplying those straight across, we get 1/4. So our first multiplication rule of probability is this. We say when two events, and we could extend this to more than 2 events, but specifically in this case, when two events, A and B, are independent of one another, that is, A does not affect the probability of B occurring, we say the probability of both occurring, and I should say in sequence, is this right here, where we say A is the first event and B is the second event, but probability of A and B. And you'll notice that all I've done here is essentially replace the and with the multiplication sign, and then I've worked these probabilities of the first event and the second event individually. We call these simple probabilities because there's only one probability in the parentheses here. So let's go ahead and put our multiplication rule to use here. I'll show you how easy it is to deal with this. But let's say a coin is flipped and a die is rolled. And it says, let's find the probability of getting a head on the coin and a 4 on the die. And I don't know if you noticed this here, but I put this in italics for a reason, because we're indicating something that happened in sequence. So if you want to know what probability you're finding, you should always write that first. Read the last sentence. Usually it's right there. But the probability of getting a heads. So we're going to write probability of heads, and then we'll say and what we want to do here is roll a 4 on the die. So essentially we have this coin that could land on either side, and we have some die, some 6-sided standard die here that could roll a 1 through a 6, here, depending. But we say, well, using our multiplication rule, we recognize that and would mean that these things are occurring in sequence. So what this means is we could take this compound probability of more than one event occurring in a time here and split it up into probability of the first thing times the probability of the second thing. And now we get this probability, set of probabilities here. And all we need to do now is just really work out the likelihood of each individual thing and multiply them together. So the probability we get a heads in the first place is, of course, 1 and 2. And the probability we roll a 4, well, there's only one 4 on a die out of 6 possible outcomes. So we say multiplying these straight across, there's no reduction that we can do here. We get a 1 in 12 probability. And as a matter of fact, it is very appropriate a lot of the times in probability to also give a decimal value for this. So I'm going to work this out. And moving the decimal twice to the right here, we'd say that this equals 0.083 repeating, that this is as a percentage, this is 8.33 repeating percent. So not a very good chance, but this is how you would work it. So now let's take a look at these last two examples. We say a card is drawn from a deck, and this is a key word here. Then we replaced it, and then a second card is drawn. The reason why replaced is a key word here is because if you did not replace that first card, then we would be talking about dependent events. The first card not being put back would affect the probability of that second card being drawn. So the probability of two events occurring in sequence that are independent of one another, we want to find the probability of getting a queen and then an ace. So again, reading this last sentence here, I noticed that we want to get a probability of a queen, and I'm going to write and to denote sequence here, and then we say ace. So this, again, we could split this up and we could say, well, it's the probability of getting a queen times the probability of getting an ace. I'll just write an A there. So just working these out individually then, what we see here is essentially this. We say, well, there are 4 queens in a deck, and there are 52 total cards. So it's a 4 in 52 chance. And the same thing with the aces here. We have 4 aces in a deck, but there are still 52 cards because we put that first card back. We put the queen back after we drew it. So I want to, if at all possible, reduce things where we can. So this is 4 goes into 52 13 times, and it goes into itself once. So we get a 1 and a 13, a 1 and a 13, and when we multiply this straight across, we get 1 times 1 on top, and then we get 13 times 13 on bottom. Okay, so it's 169. So we got a 1 in 169 chance, and we do want to express this as both a decimal and a percentage. So we'll go ahead and take that 1 divided by 169 here, and we get about 0.005917, so 0.05917. And then if we scooch this decimal twice to the right, we actually get a 0.5917-ish % likelihood that this actually occurs. Okay, so this last example here is going to highlight, you hear this quite often here, marbles in a bag and drawing them out. But we have a bag that contains 3 red marbles, 2 blue marbles, and 5 white marbles. So one thing I think that would be appropriate here is we're going to kind of indicate the total overall sample space here. And what I mean by sample space is this. I'm going to kind of split this up here. But we say if we were to look at how this is constituted, what constitutes a sample space, we say red marbles we have 3. Blue marbles, we'll put a B here, we have 2, and then the remaining are white, okay, white, and these marbles are 5 in number. So we'd say overall, and let's write this in the bottom right corner here, we have N, which represents the total number of things here. We're going to write 10 objects. So what I want to know is this, a marble is selected, and it's color noted, and then we replace it. So again, we put it back, and then we find, we draw another marble. Essentially what we're saying is by putting that first marble back, we don't affect the probability of the second marble being drawn. Okay, it doesn't affect that probability. So what's the probability we draw 2 blue marbles? The thing here is that I want to recognize this. When we say 2 blue marbles, we really mean that what we're doing is we're drawing a blue and then a blue. So the word and is very key here. And we say, well, the probability of blue and a blue is a probability of blue times blue. These are independent events. So now we say, well, what is the likelihood that we grab a blue out of this bag? And so, of course, we say that there are 2 blue marbles, and out of 10 total, so it's a 2 in 10 or a 1 in 5 chance. And the fact that we put that first marble back means that there are still 2 blue marbles the second time we try, and there are still 10 overall marbles. So again, we could multiply this straight across. We get 4 over 100, but the idea is if you can ever reduce probabilities before you do this, you probably should. no pun intended. So we become 1 in 5 in each of these instances. So 4 out of 100 would be the same thing as a 1 in 25 chance. And again, you know, you'd want to find a percentage, a decimal and a percentage for this. So 1 divided by 25 is 0.04. And so we say, since this is a 0.04 as a decimal probability, then we would say that this is a 4% chance when we move this decimal twice to the right. So let's look at a couple of different probabilities here. That's when you grab two blues, which would be hard to do, you know, not very easy because there aren't very many blues. What if we grabbed a blue and then grabbed a white? Now the fact here is this. We need to start by writing this probability. We say a blue and a white. And we can go ahead and split this up. We say probability of blue times the probability of a white. And we know that we're putting marbles back here, so we'll work these probabilities individually. So we have a 2 out of 10 here, and then a white would be a 5 out of a 10. But you notice how this gets to be a better chance. We just have more white marbles in this bag. So we'd say, well, reducing both of these individually, this becomes a 1 in 5 up front here. And we say a 5 out of 10, this becomes a 1 in 2. So now multiplying these straight across, this becomes a 1 in 10 chance, which, by the way, I don't need a calculator to do, is a 10% probability, a 10% likelihood. So that was a lot better, chance of occurring than the first probability, just because we have more white marbles, which would, contribute more to the numerator of this product here. So now let's consider this. How about a red and then a blue? Now I notice that a red, there are only 3 of those and 2 blue marbles. So what I think is this. I think that this is going to be a better chance than grabbing 2 blues in a row. But I also think that this is going to be worse than grabbing a blue and a white because there were so many whites. So again, we'll just go ahead and figure this out here. Or maybe you should. Maybe you should pause the video or skip ahead once you've figured it out and see if you got this right here. But we're going to start by writing this first as a product of 2 probabilities. So we say probability red times probability blue. And so we say the probability that we get a red is a 3 in 10 chance. And we say the probability that we grab a blue is a 2 in 10 chance. And we say, okay, well, let's reduce this one over here. We get a 1 in 5 times a 3 in 10. So on top we get 3 times 1 is 3. On the bottom we get 10 times 5 is 50, of course. So a 3/50ths chance, 3 divided by 50 here, gives us a 0.06 as a decimal probability or likelihood, which really is a 6% probability expressed as a percentage. So in the next video we'll talk about how we can extend this to 2 or more events. Okay, cheers.